In the last few lectures, we were looking at how we can employ correlations in balance equations. The typical configuration we considered was that of a sphere, for example, which is placed in a fluid, and the temperature of the sphere is initially higher than the temperature of the fluid, and then it cools with respect to time because of either conduction or convection. In this case, we have correlations available for predicting the heat transfer rate from the sphere under different conditions of either diffusion dominated or where there is forced convection or natural convection. In each of these cases, the correlation is derived assuming steady state. That is, that the temperature of the sphere is independent of time and the temperature far from the sphere is independent of time. For example, the Nusselt number is equal to 2. Correlation is determined assuming the temperature of the sphere is a constant and the temperature far away is a constant. This, on the other hand, is an unsteady problem. We can use a steady state correlation for an unsteady problem only when the time scale for the change in temperature of the particle is much longer than the diffusion time. Diffusion time is a length square divided by the diffusion coefficient, where the length is the characteristic length in the case of low Peclet number diffusion dominated transport. In that case, the provided the time scale for the decrease in temperature is much longer than this time, you can assume that at each instant of time the temperature field instantaneously assumes its steady value, because the time taken for it to reach the steady value is much smaller than the time at which the temperature is varying. And based upon that, we had derived balance equations and solved these balance equations in order to determine the time variation of the temperature. And these balance equations ultimately they contained a characteristic time, okay, for diffusion for the variation of the time scale. Okay. If you recall, in this equation for the conduction from a sphere at low Peclet number, we had derived this characteristic time, okay, and then compared that with the diffusion time. Similarly, for the dissolution of a particle, okay, there was a characteristic time, and this characteristic time was the dissolution time, and we had compared it with the time scale for diffusion. At high Peclet number, the diffusion length, the distance over which there is a disturbance to the temperature field, is much smaller than the characteristic distance, characteristic length scale of the object. The reason is because you have flow which convects mass or energy downstream, and there is diffusion from the surface. If in the limit of high Peclet number, the mass or heat that diffuses from the surface is rapidly convected downstream due to the flow, and therefore the disturbance to the temperature or concentration is restricted to a thin region close to the surface called the boundary layer. And I had given you the expressions for the boundary layer thickness. Typically, rigid surfaces it's minus 1/3, mobile surfaces with zero stress condition it's a minus half, P power minus half, in the limit of high Peclet number. That is the diffusion length. For falling film and for pipe flows, you have P power minus half times the thickness by length to the minus half, or P power minus 1/3 times diameter by length to the minus 1/3. In each of these cases, this length, characteristic length, becomes comparable to the thickness for P power for H by L comparable to P power inverse, or for H by D comparable to P inverse. Okay. I am sorry, H by L comparable to Peclet number. If H by L is comparable to Peclet number, this ratio is approximately 1, and beyond that length scale, the flow is no longer convection dominated, okay, it is diffusion dominated. And we had solved some problems in this case as well, assuming that the flow is laminar and in this case we got time constants as well. Okay. Natural convection, the length scale goes as Grashof number power minus 1 by 4. Okay. Nusselt number goes as Grashof number power plus 1 by 4. The thickness goes as Grashof number power minus 1 by 4. Okay. And in this case as well, we had solved for the problem of heat transfer from an object. There once again there is a characteristic time scale, and we had derived an expression for this characteristic time scale, okay, from the correlation. I had also solved for you a spatially varying problem for the heat transfer from a fin. In this case, there is a temperature variation along the length at steady state. We can apply the correlation locally, provided the boundary layer thickness around this, okay, the thickness of the boundary layer around this object, within which there is a variation in temperature due to natural convection, is much smaller than the length of the fin or the characteristic length scale for the variation of temperature. And that characteristic length scale, once again we had determined in terms of the flow properties and the equivalent diameter. Okay. So, this completes the discussion of forced convection, natural convection, the use of correlations. Okay. Before we proceed, I would like to discuss one problem, that is, how do you use correlations for a packed column. Okay. Recall that a packed column is packed with particles, okay, through which there is a velocity v free stream, okay, for the fluid to pass through. Okay. The free stream velocity for the fluid to pass through, and locally at any location, okay, if I expand this out, this consists of spherical particles that are packed close to each other, and there is fluid flow through the interstices between these particles. Okay. 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 There is fluid flow through the interstices between these particles. The length and the cross sectional diameter of these the characteristic diameter of this packed column is much larger than the diameter d of the particles. Okay. So, you have a very large number of particles. Okay. Now, for example, if you have a heat transfer problem where there is a fluid flowing through this packed column, the temperature of the fluid decreases, okay, as it transfers heat to the packing, for example. Okay. Or in case the fluid is being heated by the particles, the temperature increases as it transfers fluid. Okay. And therefore, the temperature is a function of distance. Okay. So, if I call this as the z coordinate, the temperature is a function of z. The correlations that we had derived did not consider this variation. They were derived for the entire column, okay, where it was assumed that the packing had one particular temperature or concentration, the fluid had another temperature or concentration. Under what conditions can we use those correlations? In this case, where the temperature is varying. Obviously, it can be used only when the length scale for the decrease of temperature. Okay. So, if I plot the temperature, for example, as a function of height, okay, so this is the z coordinate and this is the temperature. Okay. The decrease in temperature will take place over some length scale. Okay. The decrease in temperature will take place over some length scale. So long as that length scale for the decrease, I will call that the characteristic length. The characteristic length for the decrease in temperature, as long as that is much larger than the particle diameter, then I can use the assumption that locally use the correlation for the case where the temperature is a constant in the fluid and another constant in the particle. That is, neglect the variation, provided the particle diameter or the microscopic length scale in this case is much smaller than the characteristic length. So, let us solve a problem for this. Okay. In a heat recovery process, water flows upwards through column made of wax particles of diameter 1 centimeter. Okay. This paraffin wax is what is called a phase change material. Okay. So, when it melts, it will absorb latent heat, and when it freezes again, it will release this latent heat. Okay. So, you can heat it up during the day, for example, when the temperature is higher, and then that heat is available for you later at night when the temperature decreases. Okay. So, these are what are called phase change materials that can store heat. Okay. The surface temperature is the melting temperature. Centigrade. Okay. If the inlet temperature of water is 20 degrees centigrade, estimate the length of column to heat water to 75 degrees centigrade at outlet, at the outlet. Okay. Okay, for water I have rho equals 10 power 3 kg per meter cubed, mu is equal to 10 power minus 3. Okay. The thermal conductivity K is equal to 0.6 watts per meter per degree centigrade, and Cp is equal to 4.2 into 10 power 3 joules per kg per degree centigrade. Okay. Okay, so that is the problem. Okay. Initial particles of diameter 1 centimeter, that is the equivalent diameter of the particles. Inlet temperature 20 degrees centigrade, outlet temperature 75 degrees centigrade. Particles have a constant temperature of 80 degrees centigrade, which is the melting temperature of the wax. Okay. So, they will be at that temperature of 80 degrees centigrade until all of the latent heat is taken out. Okay. So, how do we solve this problem? Here obviously the temperature is varying with position. Okay. Here obviously the temperature is varying with position. Okay. Therefore, at two locations, okay, at two nearby locations, okay, Z and Z plus delta Z. Okay. The temperature is going to be different. Okay. Whatever fluid is coming in at Z has a particular temperature T of Z, leaving at Z plus delta Z has a temperature T at Z plus delta Z. Okay. The rate of change of energy of that fluid. Okay. Okay, is equal to the fluid flux times the difference in temperature. Okay. Flux is per unit area. So, if I take the fluid flux and multiply it by the area, that is the total flow rate. flow rate times the difference in temperature times the specific heat. Okay. Volumetric flow rate times, okay. So, this is equal to volumetric flow rate into change in energy density, volumetric flow rate times the change in energy density. If the superficial velocity is V s, okay, and I had forgot to add that the void fraction is equal to 0.4. Okay. If the fluid velocity is V s, then the velocity through the bed is V s divided by epsilon, okay. The ratio of the superficial velocity and the void fraction, that is the velocity in the z direction is the ratio of the superficial velocity and the void fraction. The cross sectional area is the total area of the bed times epsilon, okay. So, that is the volumetric flow rate, okay, times the difference in energy between z and z plus delta z. So, that is rho Cp T at z plus delta z minus T at z. Okay. That is the total heat transfer rate from the particles to the fluid in this differential volume of thickness delta z. Okay. That has to be equal to the heat transfer rate from the fluid to the particles. Okay. So, I can cancel out the epsilon here, okay, and this will be equal to V s A rho Cp T at z plus delta z minus T at z. Okay. So, that is the transfer rate. Okay. This change in energy, okay, the change in energy, this is a change in energy per unit time, has got to be equal to the energy transferred from the particles to the fluid in unit time. Okay. From particles to fluid per unit time is equal to the average flux, okay, times the surface area of particles. Okay. Average flux times the surface area of the particles. What is the surface area of the particles? Okay. Surface area of particles is equal to the number of particles times the area, surface area of each particle. Okay. The number of particles times the surface area of each particle. Okay. The number of particles is equal to the number of particles is equal to the particle volume by the total volume. Okay. You recall that we had done this calculation when we did packed columns. Okay. N is equal to the total the number of particles is equal to the total volume divided by the volume of one particle. Okay. The total volume occupied by the particles within this differential height delta z, okay, is going to be the volume delta z into A, okay, that is the total volume, into 1 minus epsilon. Delta z into A is the total volume of that differential volume element, that times 1 minus epsilon is the volume occupied by the particles, okay, that is the volume occupied by the particles. Okay. Volume into epsilon is the void, volume into 1 minus epsilon is the particles. So, that is the total volume occupied by the particles divided by the volume of one particle, that is the number of particles. Okay. Therefore, surface area of particles is equal to AP delta Z A into 1 minus epsilon by Vp. Okay. Volume particle Vp divided by area, surface area, is the equivalent diameter divided by 6. Okay. So, I can also write this as 6 A delta Z into 1 minus epsilon divided by the equivalent diameter, which is the same as the diameter in this case, okay, because these are spherical particles we are told. So, the equivalent diameter is the same as the diameter of the particle. Okay, so, that is the surface area of the particles. Okay. So, therefore, the energy transfer rate, okay, is equal to QAV 6 A delta Z 1 minus epsilon by d. Okay. That has got to be equal to the change in energy of the fluid. Okay. That has to be equal to the change in energy of the fluid. Okay. So, equating these two, you will get Vs rho A rho Cp, okay, T at Z plus delta Z minus T at Z. Okay. Change in energy per unit time of the fluid within this differential volume delta Z, okay, as it is passing through, is equal to QAV 6 A delta Z into 1 minus epsilon by T. And the areas will cancel out on the two sides, the areas will cancel out on the two sides. Okay. And I divide throughout by delta Z and rho Cp, and I will get by delta Z is equal to 6 into 1 minus epsilon into QAV by rho Cp Vs d. And for the average flux, I can use a Nusselt number express it in terms of the Nusselt number, because I know that QAV is equal to, in this particular case for packed columns, QAV is equal to, sorry, let me just start with the definition of Nusselt number, okay, is equal to QAV by K delta T into 1 minus epsilon by d epsilon. Okay. Note that the characteristic length scale for flow through a packed column was the equivalent diameter of the voids between the particles. Okay. And we had related that, if you recall, to the equivalent diameter of the particles themselves as epsilon dE by 1 minus epsilon. Okay. And that is the factor that comes in the denominator. Okay. I have to divide that by that. Okay, so divided by, no, this is correct, I am sorry. Okay. Inverse of this length scale is 1 minus epsilon by d epsilon. Okay. And if I take the limit as delta Z going to 0, I will get dt by dz is equal to 6 into 1 minus epsilon by rho Cp Vs d, okay, into Nusselt number K delta T. Okay. This is T minus the T particles, okay, because there is heat transfer from the particles to the fluid. This is basically T minus the T particle. Note that the temperature of the fluid is a function of Z. Temperature of particles, since it is a phase change material, is fixed at 80 degrees centigrade, okay, whereas T fluid is a function of Z, okay, into 1 minus epsilon by d epsilon. Okay. I can write this as minus T minus Tp divided by Lc. Okay. So, you can include this entire thing, okay, into just one constant. Okay. And just based upon dimensional analysis, this has to have dimensions of 1 over length, because on the left side you have temperature divided by length. Okay. So, I can include this whole thing in just one constant, okay, where this characteristic length is equal to rho Cp Vs d square epsilon by 6 Nusselt number k into 1 minus epsilon the whole square. Okay. So, this is the equation and I can solve it quite easily. Okay. So, you will just get that the solution of this is that Tp minus T is equal to Tp minus Ti e power minus Z by Lc, exponentially decreasing temperature difference, okay, with height. Okay. So, temperature difference between the particles in the fluid decreases exponentially with height. Okay. So, if I in this particular case it is the difference between the particles and the fluid. Particle is at 80 degrees centigrade, fluid is at 20 at the inlet, and you want it to be 75 at the outlet. So, the difference in temperature is 60 degrees at the inlet, it has to decrease to 5 degrees at the outlet. Okay. And we have to find out the length required for that. Okay. So, length required okay. T is equal to 75 degrees centigrade, the outlet temperature. Ti is equal to 20 degrees centigrade, the inlet temperature, and Tp is equal to 80 degrees centigrade for this phase change material. Okay. Okay. So, therefore, you require that 80 degrees minus 75 degrees centigrade is equal to 80 degrees centigrade minus 20 degrees centigrade e power minus Z by Lc. Okay. Therefore, e power minus Z by Lc is equal to 5 by 60. Okay. And from this you can get Z is equal to minus Lc log of 5 by 60 is equal to Lc log of 12. Okay. Lc times log of 12 has to be equal to the total length. Okay. Z in this case is the total length. Okay. So, this is the total length. Okay. So, the Z value at which the temperature reaches 75 degrees centigrade is the total length. Okay. How do we calculate that? So, first things is we have to calculate the correlation for the Nusselt number. I had given you a correlation earlier, okay, the correlation for the flow through a packed column. Okay. I had expressed it earlier as Nusselt number is equal to 0.5 Re power half plus 0.2 Re power 2 by 3 into PR power 1/3. This was, if you recall, the Whittaker correlation that we had discussed earlier. Okay. and we can use this correlation. We have to find out what are the Reynolds number and the Prandtl number. Okay. Reynolds number, if you recall, is equal to rho V s d by 1 minus epsilon mu. Okay. Density is 10 power 3 kg per meter cubed into the superficial velocity, if you recall, was one centimeter per second. Okay. 1 centimeters per second is 0.01 meter per second. The diameter was 1 centimeter, 0.01 meter, by 1 minus epsilon. Epsilon was 0.4 void fraction. So, 1 minus epsilon was 0.6 into 10 power minus 3 kg per meter per second. Okay. And if you work this out, this turns out to be 1.67 into 10 power 2. Reynolds number is 167 for this case. Prandtl number is equal to Cp mu by K. Specific heat is 4.2 into 10 power 3 joules per kg per degree centigrade into mu is 10 power minus 3 kg per meter per second, and K is 0.6 watt per meter per degree centigrade, and this is 7. Okay. So, based upon that and using this correlation, the Nusselt number is equal to 23.96. Okay. And the characteristic length you will get if you substitute the Nusselt number into this expression. Okay. This characteristic length turns out to be equal to 0.054 meters. Okay. Note that this analysis is valid only if the characteristic length is much larger than the particle diameter. In this case, the particle diameter is 1 centimeter. Okay. So, in this case, the characteristic length is actually larger than the particle diameter by a factor of 5. Therefore, the analysis that we have done is justified. Okay. And I can substitute the characteristic length into this expression, okay, and this length turns out to be equal to 0.135 meters. Okay. If LC is 0.054, I get 0.135 as the length that is required. Okay. So that the temperature at the outlet becomes less than becomes 75 degrees centigrade, when the temperature at the inlet was 20 degrees centigrade. Okay. So, this is one example where we are using the correlation in a problem where the temperature is varying with position. The correlation was initially derived assuming that the temperature of the fluid, or the temperature difference between the fluid and the particles, is independent of position. In this particular case, we are using it for a problem where the temperature is varying with position. So, this completes our discussion of unidirectional transport in a Cartesian coordinate system. Okay. The next lecture, I will start discussing transport in a curvilinear coordinate system. First, a cylindrical coordinate system, and then a spherical coordinate system. I will continue this in the next lecture. I will see you then.